Have you ever just stopped and wondered what light actually is? I mean, really, what is it? For centuries, that was one of the biggest mysteries in all of science. But then, in 1865, the answer was finally cracked. And you know what? It wasn't found in a lab. It was found hiding inside 4 lines of math. Today, we're going to crack open the universe's source code. And here they are. This is it. This is the masterpiece. You have to understand, scientists like Gauss, Faraday, and Ampère had been working on this stuff for decades. And then, this one physicist, James Clerk Maxwell, comes along and unifies all of their work into these 4 beautiful equations. Now, on the surface, they were about electricity and magnetism, but hidden deep inside them was a secret that would completely change the game.
You know, what's really cool is that Maxwell's original paper was, well, it was a bit of a mess. It had something like 20 different equations in it. What we're looking at here is the super condensed, elegant version that physicists have polished over the years. It's just pure poetry. And to get it, we really only need to start with 2 very simple ideas.
And get this, everything we're about to talk about, I mean everything, from static electricity that makes your hair stand up to the Wi-Fi signal hitting your device right now, it all boils down to just 2 things. First, you've got electric charges just sitting there. They create electric fields. And second, you have those same charges moving. We call that a current, and that creates magnetic fields. That's it. That's the whole foundation.
Okay, so let's start with the basics. What do these fields actually look like when everything's just still, when nothing is changing over time? Well, the first 2 equations, Gauss's laws, they lay down the ground rules for static electric and magnetic fields.
And right away, we see this huge difference between electricity and magnetism. The first law basically says electric fields radiate out from a positive charge and sink into a negative charge. Kind of like water shooting out of a sprinkler head, right? They have a clear source. But the second law says magnetic fields are totally different. They're always perfect closed loops. They're like a racetrack with no starting line and no finish line.
And that leads to this really fascinating consequence. Because those magnetic field lines are always loops, you can never have a North Pole all by itself or a South Pole all by itself. It's impossible. If you take a bar magnet and snap it in half hoping to isolate the 2 poles, guess what? You just get 2 smaller magnets, each with its very own North and South Pole, every single time. So to actually measure that whole sprinkler effect, physicists came up with this really handy idea called flux. Just picture it like this. You're just counting how many of those field lines are poking through a surface. The more lines you count, the more flux you have, and the stronger the field is. It's a simple concept, but it's the absolute core of both of Gauss's laws.
All right, so we've got our static rules down. But now it gets really good. This is where the magic happens. What if we introduce change? What happens when these fields start moving and shaking and varying in time? Let's dive into the next 2 equations, because this is where the 2 fields begin this incredible, intricate dance. So Michael Faraday discovered this amazing connection. If you change a magnetic field, like literally just by waving a magnet back and forth, you don't get one of those straight sprinkler-like electric fields. No, you create a swirling, looping electric field. This one insight is the reason nearly every power plant on Earth works. It's the basis for every electric generator. So remember this part. A changing magnetic field makes an electric field.
Now, the last equation, Ampere's law, was pretty straightforward. It just said that an electric current in a wire makes a magnetic field around it. Easy enough. But Maxwell, being Maxwell, he found a problem, a flaw. The law just didn't work in certain places, like in the empty space between the plates of a charging capacitor. There's no wire, no current flowing through that gap, and yet a magnetic field appears there. So, how?
This right here was Maxwell's stroke of pure genius. He thought, okay, as that capacitor charges, the electric field in the gap is getting stronger. It's changing. So he proposed that this changing electric field acts just like a real current, and it too creates a magnetic field. He called it a displacement current. And by adding this one little term to the equation, he didn't just fix the law, he accidentally stumbled upon a breathtaking symmetry hidden in the universe.
I mean, just look at this. It's perfect. Faraday already showed us that a changing magnetic field creates an electric field. And now Maxwell's brilliant fix showed that a changing electric field creates a magnetic field. Do you see it? They create each other. It is a perfect, self-sustaining feedback loop, a cosmic dance. A changing B field makes an E field, which in turn makes a new B field, which makes a new E field, on and on forever.
And this, right here, is where everything changes.
Maxwell realized he hadn't just cleaned up some messy math. By finding this perfect dance, this symmetry, he was on the brink of making the single most important prediction in the history of physics. He just had to ask himself one more question. What would this dance look like in the complete emptiness of space?
So he took his four now complete equations and he set them up to describe a patch of empty space. Nothing in it. No charges, no currents, just a pure vacuum. And he asked, can a disturbance in these fields just exist and travel all on its own?
And the math spat out an absolutely jaw-dropping answer. Yes, the equations predicted that this perpetual dance, this changing E field creating a B field, creating an E field, would ripple out through the fabric of space itself. It would be a self-propagating wave, an electromagnetic wave.
But here's the part that'll give you goosebumps. The equations didn't just say a wave could exist, they predicted its exact speed. And that speed wasn't random. It was determined by just two numbers, two fundamental constants of nature that scientists had already measured in boring lab experiments. These numbers were basically the universe's factory settings for how electricity and magnetism work.
When Maxwell plugged the known values for those two constants into his new equation, this is the number he got, almost 300 million meters per second, a speed that came purely from the basic electrical and magnetic properties of empty space.
Now, you gotta remember, at the same time, other scientists had spent years trying to measure the speed of light using complicated setups with spinning mirrors and telescopes, and the number they kept getting was, for all practical purposes, identical to the number Maxwell had just calculated from his equations about electricity and magnetism.
This couldn't be a coincidence. The numbers were the same. In that one incredible moment of realization, Maxwell solved the ancient mystery of light. Light wasn't some weird, separate phenomenon. Light was the dance. Light is an electromagnetic wave.
So what? Right? It's a beautiful theory, but why does any of this matter to you and me? Well, because once you figure out the code for something, you can start to write your own programs with it. And believe me, this discovery didn't just stay in a physics textbook. It literally built the modern world we are all living in right now.
Seriously, every single thing on this list exists because we finally understood Maxwell's equations. Radio waves, beaming information across the planet, the microwaves that heat up your lunch, the radar guiding planes safely through the clouds, and yeah, the Wi-Fi and cell signal that are probably delivering this to you right now. It's all just Maxwell's dance. It's all just different frequencies of light that we finally learned how to speak.
What Maxwell did was one of the greatest intellectual feats in all of human history. He showed us that the universe is simpler, more elegant, and more interconnected than we ever dreamed. And it just makes you wonder, as we stare at the remaining mysteries, like gravity and the weirdness of the quantum world, what other fundamental codes of the universe are we on the verge of cracking right now?